Let's take a look at two very similar integrals, 1 over x plus 3 squared and 1 over x plus 2 times x plus 3. They're very similar because really on the bottom you have two factors. It's just in the first integral here the factors are the same, and in the second one they're different. However, this subtle difference will give us another completely different approach to consider for these types of integrals. For the first integral here, what we can do is apply a simple substitution. If I let u be x plus 3, I should be able to carry out the integration of the first integral. For the second one, however, there's no substitution that would work. If I let u be x plus 2, then the x plus 3 term will have to be written in terms of u, and it will still leave me with two non-similar terms at the bottom of this integral. So the idea that we're going to explore in this lecture is to take this big fraction inside the integral and break it up into simpler, smaller fractions, the ones that I can integrate one at a time. This process of first breaking the fraction up and then integrating is what we will call partial fractions decomposition. So let's see what are the procedures behind that. So first of all, what are the fractions that we might be able to break this fraction, this big rational function, into? Let's think about, for example, something like 1/6. If the denominator is a product of two things, like in this case it's a product of 2 and 3, that means that likely, or we could hope so, the fraction can be composed of two fractions, one with denominator 2 and one with denominator 3, and the product 2 times 3 came from the fact that we were trying to do common denominators. Similar idea here. This is a product of two factors, which means that one would hope that the fraction came from two other fractions, one with denominator x plus 2 and one with denominator x plus 3. Now, what actually goes on top is something that we're going to have to be careful about. The coefficient, or rather the unknown that we put on top, is going to always be a polynomial that is 1 degree less than the bottom. So here, both of the bottoms are linear functions. 1 degree less is a constant. So for both tops here, I have to introduce constants. They don't have to be the same, so I'm going to give them different names, A and B. What I'm going to do next is actually do the common denominators on the right-hand side here, and then compare what I get. So if I were to put these two fractions together, then I would, of course, have to multiply the first fraction and divide it by x plus 3, the missing portion of the denominator, the one part that is not included in the current fraction, and I would have to multiply the second fraction by its missing denominator factor, namely x plus 2. So putting the actual common denominators together, I'm going to have a times x plus 3 plus b times x plus 2 all over x plus 2 times x plus 3. Now, there are actually a number of ways to proceed from here, and I will show you one and discuss another one. You might find different approaches in other books or other materials. How you proceed from now on is really up to you. The idea, though, is that if I compare the leftmost and the rightmost expressions, I notice that the denominators are the same, which means that since these expressions are equal, the numerators have to be the same. So somehow this one needs to be equal to this entire numerator here. And now the question really is, how do we generally compare polynomials? This is a polynomial of degree 0 because it's just a constant. This is a polynomial of degree 1 because I can see that x occurs to degree 1 throughout. How do we compare two polynomials and decide whether they're equal or not? So for example, if you were comparing 4x squared plus 3x versus 4x squared plus 4x, would you say they're equal? Why or why not? How would you proceed with your comparison? Well, more likely than not, you will compare coefficient by coefficient of the corresponding power. So the x squares here have the same coefficient, which is 4, whereas x's here have a different coefficient, 3 versus 4, which means that these two polynomials are not equal. We're going to do the exact same thing here, except for we're going to compare something that we know every coefficient of versus something where some of the coefficients are given to us by constants. Now, in order for me to compare powers of x, it's probably best to first organize this numerator into powers of x. So I'm going to open up the brackets, and then I'm going to collect terms per powers of x. So here I notice that I will have x that will appear in ax and then bx. So the coefficient in front of x is actually a plus b. And then I no longer have any x's, so what I have left are constants. And the constant will be 3a plus 2b in this case. 3a plus 2b. Now the denominator, of course, doesn't change and is equal to the one on the leftmost side here. So this is where I have to go. So again, let me just reiterate, the tops must be equal in order for these fractions to be equal to each other, which means that 1 must be equal to x times a plus b plus 3a plus 2b. Now, what does that mean? Let's compare power by power. So here I notice that I essentially have two types of powers. I have a coefficient for the power of x, and I have a coefficient for the power of x 0, which is of course 1. So in terms of x's, let me actually label it like that, what do I have? I'm going to see what do I have in terms of the coefficient of x's on the left versus what do I have on the right. Do I have any x's on the left? Well, no, I don't, but that really just means that I have 0 times x plus 1, so the coefficient in front of x here is 0. So this is my coefficient of x on the left. What is my coefficient of x on the right? Well, here I can clearly see that the coefficient of x is a plus b. Now, the other things that I have, and this is kind of easy to spot using the right-hand side, I have accounted for this term. I have not yet accounted for this one. This second term has no x's. So these are what I can call my ones, or what I can call my constant terms. So these are constant terms. What do I have on the left for constant? I have 1. What do I have on the right for constant? On the right, I have 3a plus 2b. So now what I end up with at this point is actually really useful information, because I have two equations in terms of a and b that I can solve together. I have two equations, two unknowns. These two must be solvable, and I should be able to find the values of a and b that work. Now, there are a number of ways to proceed from here as well. Again, it really depends on how you prefer to solve systems of linear equations. For this one, for example, what I can do is solve the top one for one of the unknowns. Let's say from the top one, I can note that b is equal to minus a, and then I can use this fact to replace b in my second equation with minus a. So then if I plug this into the second equation, I'm going to get 1 is equal to 3a plus 2 times b, but b, as per my first equation, is actually negative a, so I can plug this into here. This will, in turn, give me what? I have 3a minus 2a, which is just a, is equal to 1. So this is great news. I already have the value for a, and then I can plug this back into my first equation here. If a is 1, then minus 1 is what b is going to be. So this also immediately gives me that b is minus 1. So now I have my value for a that I can use up here and value for b that I can use up here. So I've managed to take a big fraction and split it into two smaller fractions with much simpler denominators with known values for a and b. Now, before we see the next step of how to proceed, let's discuss this process one more time. So what I did was assume that my fraction can be split up into these two, but with some, for now unknown to me, numerators. I then took all of that and actually brought the common denominators back together. Then I formed the numerator by powers of x, and then I actually compared powers of x. What did I have in terms of x to power 1s, and what did I have in terms of x to power 0s? Once I was down to these two equations, I was able to solve for a and b separately. Now that I have that, again, let's plug these values back into here and see what we get. So according to this, what I actually have, I can put the integral in front of it now. What I've discovered is that this fraction is equal to a, which is 1, over x plus 2, plus b, which is minus 1, over x plus 3. This is what my decomposition gave me. Now, integrals can be split over the plus sign, which now means that I can integrate these two fractions separately. 1 over x plus 2 dx, and then I can, of course, move this minus down, which will give me minus the integral of 1 over x plus 3 dx. Now, at this point, you can either use the substitution for each one of them. The substitutions are going to be different, but the same type of substitution for each one. Or if you've done the substitution enough, you would already notice that this integral is actually simply ln of x plus 2. And the second one is simply ln of x plus 3 plus a constant. Okay, so again, if in this step you require a middle step here to perform a substitution and then see how this is equal to the logarithm, by all means do that step. Otherwise, if you've practiced a substitution enough that you can spot patterns that lie within it, you should be able to produce the final answer immediately. Now, of course, you can simplify this answer a little bit further by actually applying logarithmic rules that will allow you to combine the two things together. So this will actually be ln of x plus 2 divided by x plus 3 plus a constant, but you can leave it in this form. Once you've performed your integration, the answer is as final as it needs to be, really, if it's in terms of the original variable, that is. Okay, so this is how we can proceed through this process. There are, as I mentioned, even within the process itself, when you are setting up this system, there are a few different nuances or slightly different ways that you can proceed to actually evaluate values for a and b with. For example, one of the fairly common methods discussed in some of the books would be to pick values for x and plug them in. This equation is supposed to work for any x that you pick, so pick a value for x. If you pick a 0, you will actually end up with an equation 1 equals 3a plus b, the second equation here. If you pick something else, like x equals 1, you will end up with yet another equation for a and b. Something like this will always work as well. This method that I'm describing here is considered the most standard and the most commonly used, and that's the method that you will see described in our textbook. So now let's see a few other examples of how this can be worked out. Here I have compute x minus 1 divided by x squared plus 3x plus 2. So what I notice is, again, immediately it's not obvious what to use. If I use a substitution, I would probably try to substitute for the denominator, but then as the du, I will get 2x plus 3, which doesn't look like anything else in the integral. So my substitution is not going to work very well. So the next thing to think about is, can I factor the bottom out? So here, let's think about the integral, but in terms of simplifying it first of all. Can I factor out this quadratic? Well, if you look at it for a few seconds, you will recognize that this is x plus 2, x plus 1, dx. And once I have this, I already know that I will probably be using partial fractions because on the bottom I have a product of two polynomials. Now, the one small caveat to partial fractions decomposition is the fact that if you are to use this method, the actual fraction you're using it on has to be reduced. This means that the degree of the top has to be less than the total degree of the bottom. So for example, if here on the top I had x cubed, I wouldn't be able to use partial decompositions. I would first of all have to divide through to sort of separate the whole part. It's kind of like thinking of 5 quarters. before I can really do anything with it, I have to take down the 5 and turn this into 1 plus 1/4, and then think of whatever fraction remains that is an actual fraction, a proper fraction. Now here, the total degree of the top is smaller than the degree of the bottom, so I know that I can proceed with partial fractions decomposition. Now notice that in the partial fractions decomposition, in the first step, I will be only working with what's inside the integral, so I'm not going to continue with the integration for now. I'm going to drop the integral sign and then sort of do this side work of working out what the inside of the integral can be rewritten as. Now, as in the previous example, that means that I'm looking at denominators x plus 2 and x plus 1. Now, I've mentioned this before, and this is what we're going to spend quite a bit of time on the next slide as well. The things you put on top here have to always be, 1 degree less than the polynomial on the bottom. So in both of these cases, the polynomials on the bottom are again linear, which means that what I put on top are constants. So this case, like the last one, is still just the constants. Now, what I strongly urge you to do here is pause the video, really, and work out the rest of this example in the exact same manner as the previous one. These two examples are extremely analogous, and this is really meant for you as an exercise to try out the method. Follow the logic in this example here of splitting it up, bringing the common denominators together, comparing the powers of x, solving for a and b, and then integrating. Once you go through that, come back to the video to see if your method and if your values that you ended up with are the same as mine. Okay, pause right now. So let's assume that you were good students and actually did what was asked. Here, once we bring everything together, what we're going to end up with is, well, I suppose I don't have to really skip too many steps, ax plus 1 plus b times x plus 2 all over the common denominator x plus 2 times x plus 1. And again, it's actually better to group these by powers of x. So in this case, I will have x times a plus b plus a plus 2b, and then the same denominator I always had. Once I'm down to here, I now know that tops have to be equal, so that is what I will be comparing the powers of x on. Tops must be equal. Let me be thorough here. X minus 1, therefore, must be equal to x times a plus b plus a plus 2b. And now I will be comparing powers of x. If I compare x to power 1, on the left, I can see that here's x to power 1. The coefficient in front of it is simply a 1. And on the right, the x term is this one right here. The coefficient in front of it is a plus b. If I compare x to power 0, or constants, what I get on the left is, of course, negative 1. And what I get on the right is the portion that has no x in it. So a plus 2b. And as before, I end up with 2 equations and 2 unknowns. You can solve the 2 equations any which way you like. Here, for example, I can notice that if I subtract the 2 equations from each other, I will actually end up with something really simple, because I will have a's cancel out, and then b's will immediately give me an answer. So if I subtract 2 equations, I will immediately get that 2 is equal to minus b, which means, of course, that b is equal to minus 2. And if I plug that back into one of the equations, I can calculate the value for a. A here will work out to be 3, which means that now I know that a is equal to 3 for this expression here, and b is equal to negative 2 for this expression right here. So now, this is kind of like your side work, your rough work that you're doing for the integral. I can come back to my original integral to rewrite it in this format. So what am I going to have here? let me create a clear separation here between the two. And what I'm going to have is that my original integral is then equal to the integral of a, which is 3 over x plus 2, plus b, which is minus 2 over x plus 1, all with respect to x. Now, as before, I can, of course, split them up with the plus in the middle and then integrate one at a time. Notice here that I actually have constants, so I have to be mindful of that, but altogether, the result of my integration will then be 3 times the antiderivative of 1 over x plus 2, which is just ln of x plus 2, minus 2 ln of x plus 1 plus a constant. So notice that in this example, the approach is exactly the same. We break up the fraction into as many pieces as needed that are all simple, and then we're able to integrate it one at a time. Now, the only differences will be in what types of functions we are breaking our big fraction into and how we are going to actually compare, what coefficients do we get by comparison. Now, really, the hardest step is the first one, deciding what to break the fraction into, because everything else is really a fairly straightforward algebra. It doesn't mean that it's super easy or fast, but it is fairly straightforward and can be always accomplished by simple, careful calculations. This first step, however, is something that we need to focus on just a little bit to make sure that it is properly analyzed. So let's take a look here what happens when our denominators are different and potentially of higher powers and more complicated. Also remember that the one caveat to the partial fractions decomposition was the fact that the power of the top has to be lower than the power of the bottom in order for us to proceed with the method. Otherwise, we have to use long division first. Now, this is not Math 112, and in this course, I will not concentrate on actual long division if necessary, as you will notice in all examples here, and in those that are on web work, we will always have the fraction in already reduced form and therefore ready for partial fractions to be performed. Now, what you are also watching out for is what are the degrees of things on the bottom and therefore what the degree of the top unknown part is supposed to be. In our first two examples, the bottoms were linear factors, and as I mentioned, the tops always has to be 1 degree less. In both of these cases, they were simply constants. On this slide, we will consider higher powers. Now, this would be just the first step in the integration. So if these were all integrals to be evaluated, first you will perform the partial fractions and then the integration itself. On this slide, I'm only going to do the partial fraction setup because, again, this is not only the hardest step, it's also the only step that is actually different from other integration techniques. So let's take a look at this first one here. I have x minus 1 divided by x squared plus 1. If I am to break this up into fractions, that means that I have to factor out the denominator. Now here, though, it's x squared plus 1. If I want to factor it out, I can also set it to be 0 and see what the roots are. But if I set it to be 0, I next end up with equation x squared is equal to minus 1, which of course has no solutions because nothing squared can ever be negative. That means that my denominator cannot be broken apart to begin with, which means that this fraction simply has no decomposition. And in fact, if I were to have an integral of this rational function as something that I wanted to evaluate, here a simple substitution would actually do. So I urge you to try to substitute u for the bottom and see how you can manipulate the top to then make that substitution work. For this next one, what do we have? I have that the bottom is already factored out for me, and I in fact can see 3 different linear factors. So the breakup here would be some constant divided by the first linear factor. Don't let this confuse you. This x is actually, if you prefer, you can rewrite this x as x plus 0 and then see that it's a linear factor like any others. So my first linear factor will be something over x plus something over x plus 1. And again, being the 1 power less than the denominator means that the top here will have to be constant. And then something over x plus 2. Same thing here. Because the denominator is linear, the top will be a constant. What have we here? Here I have one term that is linear and one term that is quadratic. Now notice that this quadratic is different from, for example, the quadratic in the previous slide, because the quadratic in this previous slide here was in fact factorable. I could factor it out into two linear factors. Whereas this quadratic here, as discussed in part 1, is not. This has no solutions, no roots. I cannot break it up any further. This is also known as an irreducible quadratic, which means that if I am to break up my fraction, this will have to stay as one piece. So now that means that when I'm breaking it up, my denominators will be x and x squared plus 1. Now recall, again, what goes on top has to be 1 degree less than what's on the bottom. Here, the degree of x is 1, which means that what goes on top is going to be, in fact, a constant. But here, I have x is of degree 2, which means that what I have to put on top has to be linear. What is the most general form of a linear function? Is it something like bx? Not quite, right? If you think of the most common way that we can write, or the most general way that we can write a line, it's not a line like this that will inevitably go through the origin. It's a line of the form something x plus something else. So this is what we have to put on top here. The most general looking linear function is a line of some slope with some y-intercept. Now the next example is slightly different from the one above. I also have two terms, but this first one appears to power 2. So let me actually think first about what are the terms as we go along. I have a term x, then x squared, and then x plus 3. So this x squared packs within itself a linear term x and then a repeated power on it. And this has to be taken into account. So what we're going to do for things like this is work our way up to the power. So if I have x squared, that means that I will have to break it up into just x and then x squared in order to, as I said, work our way up to this power. And then my third term here is going to be simply x plus 3, because that's my other separate factor here, and here we go. Now here I see that my actual terms are linear, and this factor of 2 has to be treated only as a repetition of what I've already seen. The term itself is linear. The factor, or rather the power of 2 is an add-on. Notice here that the term itself is quadratic, and there is no power added to the top of it. So what we care about is the inside power of all of these terms, which in this case is all linear, so the things that go on top for this decomposition will all be simply constants. Now the last example packs a lot of punch here. There's lots of things going on, and we're going to have to be super careful about that. So my first term here, x squared, so we have x as the actual inside and the power of 2 that we're going to work up to. So now I'm going to have x and x squared as denominators. However, because the terms themselves are linear, the tops are going to be simply constants. What else are we going to have? The next one is x plus 3. But it is also to a power. So I'm going to have to work my way up to this power of 2 with a linear term x plus 3. So I'm going to have x plus 3 and then x plus 3 all squared. But once again, because the term itself is linear, the top has to be 1 power less than that, which will mean that the tops for both of those are going to have to be simply constants. And then finally, I have x squared plus 2, which, as we've already discussed, is not reducible, and therefore I will have to leave as is. Now, in itself, it's a quadratic term, which means that what goes on top here has to be linear. What am I up to alphabetically? A, B, C, D. So my line here will then be EX plus F. Think about what would happen if this term 2 was squared. How would you have adjusted the end of this decomposition? There's a couple of questions on WebWork that require you to do just that. As I mentioned, this step of setting up what the partial decomposition looks like is likely the hardest of the entire process, and therefore something to be practiced separately. Next, we're going to take a look at a really interesting application of partial decompositions in nature. We're going to talk about sterile insect technique. Sterile insect technique is a method of biological insect control that basically consists of releasing an overwhelming amount of sterile insects, most likely males, into the wild. The idea is that the females mate with the sterile males, produce no offspring, and therefore the population reduces drastically or simply dies off. This idea was actually first introduced in the 40s by a Russian geneticist Serebrovsky, but the first very extremely successful use of it was actually in 1954 to eradicate screwworm flies from the island of Curacao, which is off the coast of Venezuela. These flies were eliminated in 7 short weeks because their lifespan and their mating cycles are so short that the introduction of sterile males into the population ended up in eradicating the entire population of flies in 7 short weeks, which actually saved the domestic goats that were the main source of meat and milk for the population. Now, we don't know of any side effects of eliminating this pest from the population, and therefore we consider this to be an ecological success, but there, of course, might be other processes that we are not tracking that might have been somehow detrimentally affected by now the absence of these flies. Now, what is fascinating is the fact that we can actually produce an integral that relates the time and the female population of the flies. Let's take a look at not the derivation is a bit technical and partially experimental, but rather at what are the variables involved and what kinds of calculations we can actually do with the model that we have. P here will represent the number of female insects in a population. Now, the number of female insects actually only grows with production of females by females. And therefore, we would like R to be representing the per capita rate of that production. Now, S will represent the number of sterile males that are introduced within each generation. The number of sterile males, of course, doesn't change because whatever females produce, if they produce a male descendant, the freshly produced male descendant will be non-sterile. So the idea here is that some things remain constant and some things change. What we would like to figure out is how does the female population change? Because the female population is the one that produces the next generation and therefore has to basically be shrinking the entire time for the insects to be eradicated. So what we have here is the integral that is connecting time of how the population grows and the female population within the time. I'm going to keep the 10,000 females as my P here. The R is going to be given by 1.1, just so we can compute with some example. And 900 will be the number of sterile males added within each population. So what we would like to do is figure out what is the actual value of this integral. So let's plug in the known values into it and then calculate. Notice that the 10,000 females are the females that we start with. So the integral is given in terms of the changing population of the females, as again, females actually do produce non-sterile females, and none of the females are ever sterilized. So I'm going to plug in the other numbers into the integral and then evaluate with it. So let's go through. This is the same integral as on the previous page. And what I have was p plus s, which was 900, divided by p times, now we have r minus 1. R itself was 1.1, so actually 10% increase in the female population within each single generation. So r minus 1 will be 0.1, p minus s, which is 900. And this whole integral is with respect to p. Now notice here that what I have on the bottom is p times 0.1 p minus 900. So what I have are two factors, and the actual degree of them on the bottom. If I open up, I notice I'm going to have p squared on the bottom, p on top, which means that I can apply partial fractions decomposition. I'm going to skip the actual algebra of setting it up, and I will only state what my decomposition will be and what would be the numbers that I derive at the end. I encourage you to fill in the middle steps to make sure that you can go through the motions of actually evaluating the constants themselves. But here, my two denominators will be p and 0.1p minus 900. As is usual with real-life applications, sometimes the actual numbers will work out to be kind of ugly. Here you can treat this denominator as is, or you can also factor out 0.1 so that you don't have a coefficient in front of p to work with. Both of them should end up with the exact same final sort of answer and final approach. Now, because the powers of both of these are simply 1, the numerators will be simply constants, a and b. So I'm going to skip the few steps that you will need to perform in order to calculate the values of a and b, but the values you should get is a is -1 and b is 1.1. So what does that mean? Recall that this integral is what stood for time in relation to population. So what we're going to have is that my time integral is then equal to a over p, so -1 over p dp plus this second integral where I have b, which is 1.1, divided by 0.1p minus 900, all with respect to p. Now here is again where I'm going to remind you that you can of course do the substitution here, and in fact the numbers here are so ugly that I strongly encourage you to go through the extra step of in fact doing the substitution for the denominator, so you are certain that the constant that comes with the du that you get is actually correct. I am going to simply state what the next step is going to be. Now, this is really the absolute value of p. Now, I know the population of my females is going to be positive, which means that I can drop the absolute value because the only things that I'm going to be interested in for the values of p are in fact going to be positive. Now this second integral will work out to be 11 ln of p minus 9,000, and that is if we actually factor things out and simplify things a little bit, and of course don't forget your constant c. Now the next question is, how do we figure out c? Well, recall that the initial condition, so at time t, the size of the female population was 10,000. So this is something that I can plug back into the formula and solve for c. Using this information, we will get that c is equal to approximately -67. It's going to be some sort of a decimal, but this is a close enough approximation of the value. So altogether, my formula, if I choose to bring together the two lns here, this is minus, so this is going to be logarithm divided at the bottom, and I can bring this 11 up to the power in here instead. What I'm going to have is ln of p minus 9,000 to power 11 all over p plus my c, which is actually minus, let's say, 67. So this is going to be my final formula connecting the size of the female population with the time if we, once again, remember, introduce 900 sterile males into every generation, and if we assume that the females reproduce males at the rate of 1.1 per capita. Now, the strange thing about this equation and about this model in general is that we cannot explicitly solve it for P. So this is why we have to go in this weird roundabout way to have the time and the size of the population connected with this equation. Notice that I can't isolate P here. Even if I raise everything to the exponential, I will still have something to solve for that has 11th power on top and power 1 on the bottom. And this is not one of the things that I can easily evaluate or solve for. So this, in this case, is the best that I can hope. Now, this integral being derived, again, both theoretically and experimentally, is actually quite effective in figuring out what size of the sterile population needs to be introduced in order to eradicate the population. So, for example, in the case of the screwworm fly, what we notice is that everything was eliminated in 7 weeks. So by the time we get to 7 weeks, the size of the population, as in our equation here, would have then had to be 0. So these numbers that we worked out with were not for that particular population, but this is how one would carry out these calculations. You can fix the time in which you would like to see the population disappear, and you can figure out the rest of the parameters that go with it.